um, last unit or the last topic that we'll discuss in terms of the transistors. The second type of the transistors is the FETs, and now we'll discuss, the basic of FETs, and you may see, some applications that are using, FETs. First of all, talking about, the FETs, what FET stands for? The field effect transistor. Now, compare with the BJT. A BJT uses both particles, to have the current that flows between the collector and the emitter. The positively and negatively particles that are used as the majority carriers that are operates, the BJTs. For an FET, they are using just a single carrier. And that's why an FET is called a unipolar, or has, a single type of carriers that it's used to have the current that flows through the transistor through the FET. Basically, there are two main types. We may discuss, I may mention some other types of FETs, but actually, derives from an MOSFET, and those are the newest type of the FETs, but we'll introduce a junction field effect transistor, or it's known as the JFET. That was, the first type of FET on the market. It's still used today, but most of the time, or between the two, most widely used is the MOSFET, or the metal oxide semiconductor field effect transistor. Okay, now let's see, what is the main difference between, or how, between an FET and an BJT. Remember that a field effect means that only, for the FETs, the depletion region, it will determine, or it will adjust actually the current that flows between the two terminals, between the drain and the source. You notice that I'm using a different terminology for the three terminals, or the three pins of an FET of a transistor. Initially in BJT, we use the base emitter and the collector, which is equivalent as the gate, the drain, and the source for an FET. Another major difference between the two transistors, an FET is a voltage control device. A BJT is a current control device. The major difference is there is actually no current, or a very low current, that is required to control an FET. Theoretically is zero. In terms of the practical value for an FET that it's used to control a transistor, an FET transistor, it's in terms of nano or a picoamp. Means that in most of the portable devices, any kind of mobile devices, what we are seeing inside is an FET, is a voltage control device. Again, it requires a very small amount of current, actually just, the voltage that it's used to turn on and off, or to adjust the current that flows between the source and the drain. And the advantage, or one of the biggest advantage of an FET, has a very high input resistance, which is trying, to compare, the high input resistance of an FET with a BJT. The BJT is much lower than the input impedance or input resistance of an FET. Means that in some applications that requires a very high input resistance, FET is more suitable than a BJT. It has, a non-linear characteristic, and that's why we are not seeing too many FETs used as an amplifier. Remember that an amplifier has to have, a linear or a constant amplification or a constant gain between the two frequencies, the cut off low frequency and between the cut off upper frequency. That's why most of the time you are seeing, the FETs as it's used in applications for a low voltage. I'm talking about low voltage like 3 volts, 2 volts, 5 volts, or less than that, in switching application. Remember that one of the applications for a BJT, it's used in linear applications or analog application, and the other application was in switching application or switching circuits. The FETs are used, most of the time or most widely used in a low voltage in switching application. Means that by simply applying a small amount of voltage on the gate, we can turn the FETs on or off. Just to give you an idea, it was invented around 1930. Lilienfeld, an Austrian-Hungarian, that time physicist and inventor, and actually it was practically built and available on the market around 1950 by the Bell Labs. I mentioned that the FETs are the mostly wide use components in integrated circuits. Again, in digital logics, we may see again the two technologies. One is the TTL, transistor logic, which is probably used in when the consumption is not a concern, and the CMOS technology. It's used in application when the consumption is required to stay, at a certain level. The main difference, or another difference between a BJT and a JFET, again, that's a junction field effect transistor. Actually, we can have, we can visualize, the FET, in having, those three terminals. The equivalent of the drain terminal, it's the collector of a BJT. The equivalent for the source is the emitter, and the equivalent, or a similar terminal for the BJT is the gate instead of the base. Means that I can put aside the equivalent or the similar terminals for the BJT. That's the base, which in FET it's called the gate. Drain, it's like the collector in the BJT, and the source, it's the emitter, or like the emitter in the BJT. You notice that there is a channel that is formed between the drain and the emitter. Now, the gate, or what is the purpose of the gate? To limit or to adjust actually the current that flows between the drain and the collector. Suppose that I'm supplying a voltage to the drain. That will be, the positive on the drain, the negative on the emitter. And you notice that if there is no voltage applied to the gain, the channel is fully open. Now we have to go back into the basic functionality of a semiconductor. You notice that actually I'm having, a junction between the gate and the substrate. You notice that the channel actually is a single type semiconductor, which has, the two metal terminals on each end, means that without having, the gain, the channel or the current that flows between the drain and the source is has no limits, or has no obstructions that it will limit the current that flows between the drain and the source. You notice that on or inside or embedded in this channel, on this substrate, it's an N semiconductor on each side. And to simplify the drawing, you notice that on the representation of the gain, it's connected just in one side. Again, that's the purpose of having a simplified representation, but physically there is a connection between the two N semiconductors. Again, that's internally done in the semiconductor. The two N semiconductors, one on each side, it will obstruct or it will limit the current that flows between the drain and the source. Again, without having any voltages or the gate voltage as being equal to 0, the current is flowing without having any restrictions between the drain and the source. Actually, at this point, I can emphasize the operation or the basic functionality of the FET that is exactly the opposite with a BJT. Again, if on BJT, if we are not applying any base voltage, there is no current. For an FET is exactly the opposite. If the gate voltage is equal to 0 or there is no voltage applied on the gate, the channel is fully open, means that I have the maximum voltage or the maximum current actually that can flow between the drain and the source. Means that when the FET is connected to a voltage source, the channel is fully open. Actually, to limit the current that flows between the drain and the source, we have to apply a voltage on the gate. This voltage has to be in with a negative on the gate. Now we have to go back and check or review the two depletion regions in the forward biased and reverse biased. Now, what do you remember from a diode? If a diode is reverse forward biased, let's say, how is the depletion region? The depletion region becomes very narrow. Okay. Now, if the diode is in reverse biased, what is going to happen? If it is in reverse bias, the depletion region becomes wider. And this is, what they are trying to use in the FETs, means that the depletion region, it will limit the the channel. It will control actually the current that flows between the drain and the source. And I put that in writing, the fundamental or the main difference between the FET and BJT. The JFET junction is reverse bias. The gate current is practically zero. Means that the depletion region is wider enough that it will block or it will obstruct the current that flows between the gate, the drain and the source. In the same way, if I'm looking for the base current, the BJT is always requires some value greater than zero. Now, if I'm looking for this this biasing for an FET, you notice that again, if there is no voltage applied on the gate, the current or the channel is fully open and the maximum current is flowing between the drain and the source. And the two possibilities having the VGG or the voltage applied on the gate as a positive or as a negative. I mentioned that we are using the voltage between the gate and the source as the reverse bias. In reverse bias, the P semiconductor is supplied by a negative voltage and the N semiconductor is supplied by a positive voltage. In terms of the notation, you notice that I'm having the VDD as the voltage that is applied on the drain. For a BJT, we use the VCC as the voltage supplied on the collector. In the same way, they choose to use a different notation for the voltage that is applied on the gate as the VGG. For BJT, the voltage applied on the base is the VBB. Now we have to make some adjustments in the notation that it's used specifically for the FETs as the VDD, VGG, and the RD for the resistance that is connected into the drain of the transistor, and the purpose of the RD is to limit the current that flows between the drain and the source. Again, remember that has the same purpose. The RD has the same purpose as the RC for the BJTs. Once we are applying, the negative of the gate source on the gate terminal, now you notice that I'm having the two voltages, and both terminals has a reverse bias, but the voltage between the gate and the source is smaller than the voltage between the gate and the drain. Now, how it will affect actually the depletion region that is created in the N semiconductor, the depletion region actually it will become wider in the on the upper side or on the D terminal of the semiconductor, and it will become a bit smaller on the side where the source terminal is connected to the channel or to the substrate. Now, on reverse bias, I noticed that, and I'm having another diagram that shows the depletion region. That's why I choose two different ways to show how the channel actually the depletion region is controlled by widening or narrowing the channel between the drain and the source by simply controlling a voltage that is applied on the gate. you notice that I'm having, the drain and the source. And due to the depletion region that is created on each side of the uh, PN junction, the channel that is uh, makes the current that flows between the drain and the source, it will be um, controlled by the voltage that is applied uh, on the gate of the transistor. As I mentioned that the JFET is normally on device, means that without applying any voltages on the gate, the device have the full current or the maximum current that can flow through the um, transistor is when there is no voltage applied on the gate. Now, on this diagram shows actually, the depletion region and shows, how the channel it's blocked or is obstructed as the depletion region becomes wider and the depletion region becomes smaller. Again, if we are choosing, to have, a voltage between the gate and the source, the depletion region becomes larger, means that we are having, the PN or the gate to source and the gate to drain in reverse bias, which will wider actually the depletion region, means that the depletion region actually can block or can obstruct the current that flows between the drain and the source. And I mentioned that the depletion region is a bit wider and it's a bit deeper in the upper side of the semiconductor of the junction that is made between the drain and the source, because the potential difference between the gate and the drain is much larger or is greater than the voltage between the gate and the source. Now that's a 3D representation or the 3D schematic or symbol for an FET. Remember that that the gate is deeply connected or embedded in the substrate on the P channel or the N channel. I mentioned that we may have a P channel or an N channel. Now, in terms of the symbol that is used for a JFET, you notice that instead of having those terminals at, let's say, 90 degrees most of the time, those terminals are straighter from the channel. One is the drain and the other one is the source. Now, if I'm looking back, in this representation or this diagram, you notice that I can change, easily, the source and the drain of the FETs, which we cannot do with a BJT. Basically, it's the same semiconductor, the N-type or the P-type, which is called the N channel or the P channel of an FET. Now, the only change that is, or the only difference between the N channel and the P channel is the arrow. Actually, if the arrow is pointed in to the channel, the channel or the FET is an N channel FET. If the arrow or the tip of the arrow is pointed out, that's a P channel FET. The only difference between the N channel and the P channel in functionality is if we are using a P P channel FET, the voltages has to be in reverse way. If for an N channel I'm supplying positive the source, the N channel has the opposite, the P channel, it will have the opposite polarity with a negative applied on the drain and the positive on the source. And in the same way, if we are applying a gate source, instead of having, the negative on the gate for an N channel, we have a positive on the gate for a P channel. That's the only difference. But remember that the symbol for an FET does not have those emitter and the collector. Most of the time at 90 degrees between the two are straight lines at 90 degrees between the channel and the drain and the source. You notice that this is like the channel, and I'm trying to emphasize it's already made, because the other symbols or the other transistor does not have that or this default channel between the drain and the source. And I mentioned that for a P channel, the voltage polarities will be exactly in the opposite way. Suppose that we have a basic circuit without applying any voltages on the gate. We are just slowly increasing the VDD, or the voltage that is applied on the drain. Simply, for small voltages, we have a straight line, means that the voltage is too small to affect or to change the depletion region, means that the BJT, it will operate in the ohmic region. Means that increasing the voltage, it will increase the current that flows between the drain and the source. And that's, the current that flows between the drain and the source. And that's why it's sometimes called the ohmic region. Means that only the voltage, it will, we may change, the current that flows between the between the drain and the source. Now, at a certain point, which is called the VP, the pinch off voltage, we have a constant current as the voltage is increased above this value. Usually this pinch off voltage is supplied, or it's given by a manufacturer in the data sheet of the FETs, which is actually the minimum voltage that can be applied to a transistor, to an FET, to have or to maintain a constant current. This is, the active region, and I mentioned that we are not using intensively. Yes, there are, some applications, but we are not using intensively as BJTs in linear applications or the analog application. For any other voltages that is above the maximum voltage between the drain and the source, which is the breakdown voltage, that's another spec that we have to take into account, the maximum voltage that can be applied between the drain and the source, which is called the breakdown voltage. That's, like the collector emitter maximum voltage, which has, the same meaning. That's the limit in terms of the voltage that may be applied on the FET between the drain and the source. Now, before I'm going to the second type, which is the MOSFET, I may go back to this observation here. You notice that, and I said that an FET, JFET or MOSFET is a voltage control device. Remember that if you have to deal with an FET, any of the two types, or actually there are more than two types, when there is a precaution and there is a different way of handling the FET devices, not only the transistors, the integrated circuits. Suppose that you have to deal with an FET, you have to use an FET. Most of the time, those FETs, JFET or MOSFET or any kind of FETs, it will be supplied by the vendor, by the supplier, with a metal ring that short circuit, all the terminals when it is shipped, to the different places. The only problem is that when we are touching, because it's a voltage control device, and I mentioned that we have to be very careful, on we are handling those FET devices, FET transistors, or integrated circuits. Sometimes you will see the FET devices, transistors, or integrated circuits that are shipped or are in like a thin foil metal bag to prevent any large voltages. Sometimes is referred as an ESD, electrostatic discharge, that may damage the FET or the field effect device. Remember that another precaution is sometimes we may have to have, a bracelet or a connection between our body and the physical ground of the bench of the circuits, and that's why it's a special way of handling those devices. Another advice: make sure you are not applying any voltages, any, let's say, input voltage to a circuit without having a voltage source connected to the circuit. Now, we can apply a voltage, for example, a few volts on the on an FET circuit, or a circuit that uses an FET. Without applying a voltage to the semiconductor, we actually can destroy the semiconductor or the FET transistor or the integrated circuit. That's why it's a special precaution, how we can handle and how we can use those FET devices. Okay. Now, going back to the second type of transistors, which is the metal oxide semiconductor field effect transistor. Most of the time is referred as a MOSFET. Basically, there are two main types. There are more than that, but at this point, there are two main types. We have, the enhancement, which is an E-MOSFET. That's, more widely used, and the D-MOSFET. Now, let's see what's the main difference between the JFET and the MOSFET. Basically, there is no junction between the substrate and the gate. You notice that in the previous type, the JFET, the junction FET has actually a physical channel and has a junction between the gate and the substrate, or the channel. For a MOSFET, there is no physical connection directly, or a physical contact between the gate and the substrate. You notice that there is a layer which is, or it will act as an insulator or a dielectric between the gate and the substrate. You notice that initially there is no channel between the drain and the source, means that without applying any voltages on the gate, without having any voltages applied on the gate, actually there is no current that flows between the drain and the source. That's one of the main difference between the MOSFET and the JFET. Initially, again, there is no channel, there is no way of having the current between the drain and the source if we are not applying a gate. The silicon oxide, that's why it's a metal, that's the gate. Oxide, that's the silicon oxide that it's placed between the gate and the substrate, means that we don't have a physical or direct connection between the gate and the substrate, and the two, or the substrate and the two channels, or the two terminals, the drain and the source. When there is no voltage applied on the gate, you notice that there is no carriers that can be used, to have the current or to create the channel between the drain and the source. Suppose that we are applying a positive voltage source, or the VGG, with a positive on the gate. Remember that the positive means that I'm having an excess of the positive charged particles, which will attract the negatively charged particles from the P substrate. Means that I'm actually inducing, or I'm actually creating a channel based on the voltage that is applied on the gate, and having that insulator or dielectric between the substrate and the gate. Actually, there is no current. The current that is flowing between the gain and the source, again, is very low, or in very low power consumption, the eMOSFET or the MOSFET technology. The symbol that it's used for the P-type and the N-type. Again, you notice that the initial or the physical construction of the P-type or the N-type has no physical channel between the drain and the source. In the symbol for the N channel, you notice that there is not a structural channel or a physical channel between the drain and the source. That's why I have a dashed line between the drain and the source. The gate is isolated between the channel and the source. That's why you don't have a physical connection, or in the symbol there is no connection between the gate and the source. The same observation if the arrow is pointed to the channel, that's an N-type. If the arrow is pointed out of the channel, is the N-channel type. Means that the only difference between, again, or the same observation, the only difference between the P substrate and the N substrate is the voltage that may be applied to the to the transistor, to the drain and the source. Again, if it is an N substrate, we have to apply the voltage with the opposite polarity. The positive goes on the source and the negative goes on the drain. Nothing else is changed in the biasing the P channel or the N channel. The other change is the voltage that is applied on the gate. Instead of being positive on the gate, it will apply or will apply a negative on the gate. The MOSFET, which is the diffused channel into the substrate. Okay, now let's have a look, between the two, and I try to put them, to compare. You notice that on the E MOSFET, or the enhanced metal oxide semiconductor, there is no physical channel between the drain and the source. For a D MOSFET, or diffuse metal oxide semiconductor, FET, there is a physical channel, a small channel between the drain and the source. Now, how we can control the current that flows between the drain and the source? By simply applying, a positive or a negative voltage on the gate. Means that we can use, the MOSFET in depletion region or in enhancement region or in enhancement mode. Sometimes it's called the depletion mode, when a negative voltage is applied on the gate, and there is a negative voltage between the gate and the source. And the enhancement mode, when we are applying the positive on the gate, means that the voltage between the gate and the source is a positive voltage. The symbol, for the D MOSFET, you notice that physically we have, a channel. Now we may use, this channel as the depletion region or a depletion mode. Means that we can have, a small current that flows between the drain and the source. If we are applying a positive on the gate, we are enhancing, we are having, the E mode or the enhancement mode between the drain and the source. Means that we may have a large current that flows between the drain and the source. And the same observation, if the arrow is pointed to the channel, that's an N-type channel. Again, is referred with the substrate that is making, and the channel that is actually created between the drain and the source. If it is an N channel, the arrow is pointed out, means that almost the same symbol with compared with the E MOSFET, except that the E MOSFET has a dashed line showing that there is no physical channel created in the substrate between the drain and the source. Now we may deal with, or we may see, some other types of MOSFET technology. You may see like a V MOSFET or a T MOSFET. Those are, let's say, the semiconductors or the FET semiconductors that it's used for power electronics, I will say that. Another type of MOSFET, you may see an IGFET. which is an isolated gate field effect transistor. Or you may see a combination actually between the FET and a BJT. That's called an IGBT, isolated gate bipolar transistor. It's again a combination between an FET and a BJT. Just to give some other one idea about some other variations of the FET and the combination between the MOSFET, FET, and the BJT technology. Any questions, guys? If you don't have any questions, have a nice Halloween. Have a nice break, recharge your batteries. On the Monday after the study week or the break week, I will return your assignment, your test, your lab report on the 9th of November, and the second test will be on Friday, the 13th of November, in the same room, B2-251. Yes, will be on this the same format. I have long type questions and multiple choice questions. Same format as test 1, 70% and 30%. Did I answer your question, Sharon? Perfect. Have a nice weekend, guys. Have a nice break and have a nice Halloween.